Howdy! Welcome to Physics Chapter 7, Lecture Number 2. Alright, today's lecture you'll need to open to page 242, and all four of the problems that I'm going to work are right together here at the end of the chapter, page 242. So let's start with 7.7. It says, using the facts that the mass of the Sun is 2 times 10 to the 30th kilograms, and the radius of Pluto's orbit is 5.9 times 10 to the 12th meters, calculate Pluto's orbital period. Okay, so for all of these planetary type problems, we're going to use the fact that what causes the centripetal force is the force due to gravity. So the centripetal force is equal to the force due to gravity. So what we have here for the centripetal force is the mass of Pluto, mv squared over r, times its velocity squared over r, is equal to the force due to gravity, g times the mass of Pluto times the mass of the Sun over r squared. Right? The two bodies are Pluto and the Sun. Okay, and we are trying to get the orbital period. Well, we know that the period is equal to the circumference of the orbit, the distance, 2 pi r over the velocity. The problem gives us r, but we don't know the velocity. But we could probably use this relationship to solve for the velocity. So let's try that. So looking here, mass of Pluto is going to cancel because it's on top in both equations. And one of the radiuses, or radii, is going to cancel. So what we have here is v squared is equal to g times the mass of the Sun over r. Okay, so solving for v, that's going to be the square root of g, 6.67 times 10 to the minus 11. The mass of the Sun is given in the problem, 2 times 10 to the 30th kilograms, all over the radius, which Pluto, of course, is really far out, so it's got a big radius, 5.9 times 10 to the 12th meters. All right, so let's go ahead and do this together in our calculator. So that's going to be 6.67, then use your double E button, second function double E, the negative 11, times 2 times 10 to the 30th. I'm going to go ahead and hit enter, so you've got a number there. Divide that number by 5.9 times 10 to the 12th. Okay, and now we've got that number. I'm going to raise that to the 0.5 power to take the square root. So the velocity is 4,755 meters per second. Now that's not the answer. It asks for the period. How long does it take Pluto to make one orbit? Now this is really just going to be an estimate because Pluto's orbit is not completely circular. So the period is 2 pi times the radius, 5.9 times 10 to the 12th, over the velocity, 4,755 meters per second. All right, so let's go ahead and do that in our calculator. We won't do this every time, but we've got 2 times, the pi button is right here above the caret, times 5.9 times 10 to the 12th. All right, and then I'm going to divide that number by 4,755. Okay, and that's a big old number there. If I wanted to get that in scientific notation, I don't know if I'd be able to change that. Let's go to mode. Hit scientific. back out of that. Let's try it again and see if it gives us. Yeah. No, that's not right. Yeah, there we go. So all I had to do is change my mode to scientific and then go and highlight the number and hit it again. But 7.796. So we could say that's 7.8 times 10 to the 9th seconds. Which that is fine. You can leave your answer in seconds, but if you're interested, that's like 247 years. So it takes Pluto a lot of time to get around the sun, which makes sense because it's way out there. Pluto is part of something called the Kuiper Belt, if you're interested in reading up on that. The outer parts of the solar system. Okay, 7.8. Says the orbital period of the moon is 27.3 days, which is 2.36 times 10 to the 6 seconds. If its orbital radius is 3.8 times 10 to the 8th meters, what is the mass of the Earth? Okay, so they've given us the period. And we know that period is 2 pi r over the velocity. Now there's no mass in this equation, and we know radius. They've given us the radius. So, and the period. So we should be able to solve for velocity and then use this relationship to get mass. Okay, so solving for velocity, we're just going to switch period and velocity. I'd have 2 pi r over t. So that's 2 pi. The radius is 3.8 times 10 to the 8th. Over t, which is 2.36 times 10 to the 6th. All right, let's do this. 2 times pi times 3.8 times 10 to the 8th. And divide that by 2.36 times 10 to the 6th. And we get 1.01 times 10 to the 3 meters per second. All right, now we can use that using this relationship we have, and we're dealing with the moon here. So what goes in F sub c is the mass of the thing that is spinning. So the mass of the moon, that's what F sub c is. Mass of the moon times velocity squared over r is equal to g times the mass of the Earth. So the one doing the orbiting is what goes within F sub c, not the mass of the Earth, over r squared. So the mass of the moon ends up canceling. One radius ends up canceling. And I have v squared is equal to g times the mass of the Earth over r. The question is, what is the mass of the Earth? So solving for the mass of the Earth, multiply both sides by r, I'd have v squared times r, and then divide both sides by g. So the mass of the Earth is going to be the velocity, what you just got, 1.01 times 10 to the 3rd. Don't forget to square it. Times the radius. That's going to be 3.8 times 10 to the 8th. Over g, 6.67 times 10 to the minus 11. Newton meters squared per kilogram squared. All right. And I won't put this one in my calculator since we did that on the last one, but that's going to be 5.38 times 10 to the 24th kilograms. And I'll go ahead and put it in So hopefully you can see this. So that's going to be 1011 squared, 1011, times 3.8 times 10 to the 8th. Oops. Let's escape that. Try that again. All right, 1011 squared times 3.8 times 10 to the 8th. All right, and divide that by 6.67 times 10 to the minus 11. All right, 5.82 times 10 to the 23rd. Oh yeah, I pulled a little bit of dyslexia there. 5.82. So sorry about that. All right, let's do the last two, and that finishes up this chapter. I really enjoy these problems quite a bit. I think it's always interesting to watch those shows on Nova, PBS, about planets, things like that. All right, 7.9 says a satellite engineer wishes to place a satellite in orbit around the Earth. If the engineer wishes her satellite to have a circular orbit with a radius of 2.1 times 10 to the 7th meters, what speed must the satellite have in orbit? So we want to know velocity. Well, we have F sub c equals F sub g. No period is involved here, so we're not going to have to. We can just use this relationship. So we have the mass of the satellite times the velocity squared over r is equal to g times the mass of the satellite times the mass of the Earth over r squared. All right, and so we want to know velocity. The mass of the satellite, so it's the one that's doing the orbiting, the mass that's doing the orbiting always cancels out. Okay, and that radius cancels. So what we have is after the cancellations, v squared is equal to g times the mass of the Earth over r. So v is going to be the square root of g, 6.67 times 10 to the minus 11, times the mass of the Earth, 5.98. You can see that's a little different than our last problem because the reason we had a little bit of error is that these orbits are not exactly circular. So the mass of the Earth, and then the radius of this satellite, 2.1 times 10 to the 7th meters. All right, we'll do this together. So it's 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th. I'll hit enter. Divide that by 2.1 times 10 to the 7th. Hit enter. And then raise that to the 0.5 power to get the square root. So that's 4358. Or you can put it in scientific notation, 4.358 times 10 to the 3rd meters per second, or 4,358. If your calculator's not in scientific notation mode, it'll just give it to you like that, and that is fine. All right, last on your own problem of this chapter. .10 says a satellite orbits the Earth with a velocity of 6.6 times 10 to the 3rd meters per second. What's its altitude? And he gives the radius. Well, if we get the radius of the satellite's orbit, we can subtract the radius of the Earth and get the altitude. So let's solve for radius. So I have F sub c is equal to F sub g. F sub c is the mass of the satellite times the velocity squared over r. F sub g, g times the mass of the satellite times the mass of the Earth over r squared. One of the radius cancels, mass of the satellite cancel, and we have v squared is equal to g times the mass of the Earth over r. Solving for r, we're just going to switch the r and the v squared. You'd have g times the mass of the Earth over v squared. So r is 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24th mass of the Earth. And then the velocity, it said, was 6,600. And let's not forget to square that. Okay, so what we have as a radius is 9.16 times 10 to the 6th meters. But that's the radius that's the distance from the middle of the Earth to the middle of the satellite. Okay, we want to know the altitude. Well, the altitude is the distance between the satellite and the surface of the Earth. Okay, so we need to get the radius of the Earth. So the altitude is going to be that entire radius, what we just calculated, minus the distance from the center of the Earth to the surface of the Earth. So that's 9.16 times 10 to the 6th minus 6.38 times 10 to the 6th. And so that'll equal 2.78 times 10 to the 6th meters. All right. So I actually years ago looked that up. It's about 1,714 miles if you're interested. Okay, that does it for Chapter 7. So the homework is just to finish up the review questions and practice problems, but I'll write those down for you. So homework number 2. You're going to do review questions on page 248, 9 and 10, and practice problems page 250. You can do 7 through 10. So 4 problems just like we just worked. All right, happy physicsing. And I will talk to you on the solutions video for this homework.